There it is. So before I start with anything that's new, just to go back and to revisit what electrolysis is. We learned for most of the chapter about what a galvanic cell is. A chemical reaction, spontaneous chemical reaction, that sends electrons from something that's oxidized to something that's reduced. They do that spontaneously. You don't need any extra help. However, if you want the electrons to go the other way in the non-spontaneous direction, that's where we're going to need a power supply or power source. Something that you plug into the wall. And like we have some of these set up today because we'll be doing an electrolysis lab on Monday. So as I mentioned yesterday, that big blue box that was in the back of the room, there's a bunch of power supplies, and many of them look different from that. But remember, they always have a positive and negative terminal. There's some other terminals on this that we won't need to use. But yeah, the terminals we'll use are color-coded generally, black and red. We'll talk about that later. But that would be a power supply, and all power supplies have a plug that you plug it right into the wall, and it will generate a current. So the spontaneous direction of electrons would go from the zinc to the copper. However, in this case, you're using some external power source that causes the electrons to go from the copper to the zinc. That's what electrolysis is. Oh, we don't have to write any of that down because we did this yesterday. This is more likely the typical electrolysis setup where you don't have to have two beakers like in a galvanic cell. You would just use one beaker, put something in the beaker that can conduct charge, and put both electrodes into that one substance. So, and when you hook the power source up to it, what this does is the power source is going to run electrons from here through the power source and over to here. Now what that means is that whatever this electrode is in contact with, something has to oxidize. If you look at the flow of electrons here, they're coming out of that electrode and back into this electrode. So at this electrode, oxidation must happen. Something has to oxidize. Something in here has to oxidize. And then as the electrons flow through and come back into here, something over here must reduce. That's the whole purpose of having a power source there, is to drive a reaction. So you've got salt. Salt is a very stable compound. It's good. It just doesn't need anything. However, this power source comes, it's kind of acting like a bully. It forces the sodium chloride to break apart. So the formation of sodium chloride is a spontaneous process. If you want to get the sodium chloride to break into its elements, that is non-spontaneous then. So that's the whole idea of what the power supply is doing. It's causing a non-spontaneous reaction to work. Now, as I mentioned yesterday, as we have just a pure salt, it's got to be melted down to a liquid too, just so the charges can flow. But when you have just that liquid salt, there's only one choice of what can oxidize. The sodium ion is already a +1 in salt. It can't oxidize. We've never heard of sodium with a +2 or +3. It can't oxidize anymore. So the sodium can't oxidize. The only other choice you have is the chloride ion. The chloride is -1, and it could have its oxidation number go up to 0. And that's exactly what it does. It goes from -1 up to 0. And you have this half reaction on your reduction potential table. Over here, as the electrons come in and cause something to reduce, it can't be chloride that reduces because chloride is already a -1 and it doesn't ever go below a -1. So the only thing that could reduce is the sodium ion. And that's what we have over here at the cathode where reduction happens. Sodium, the electrons that come in here are being taken in by the sodium. So what we would observe is at the anode, chlorine gas is being made. We would see yellow bubbles forming as chloride ions become chlorine gas. It wasn't your phone, so it's fine. And then as the electrons come in here, we would observe a soft silver-colored metal coating that electrode, because that would be the sodium. Sodium is making sodium metal, and that would coat the electrode, and we would have sodium metal. You don't find sodium metal in nature because it's so reactive. So this is one way that sodium metal could be made. Now today, what we're going to do is we're going to look at, I'm going to have to go through a couple of slides. Nope, not even that one. We're going to look at not pure salts. Am I off?
Yeah.
Thank you. Thanks for doing that. Not pure salts, but solutions that have salts in them. So rather than putting an electrolysis apparatus into just pure sodium chloride, we're going to put it in a salt water solution. And the question is going to be, when you do that, now what is oxidized and what's reduced? So these problems are not going to involve any math. You don't have to do any calculating or anything. What you have to do is just determine what happens at the anode and what happens at the cathode. Because remember, with electrolysis, something has to oxidize and something has to reduce. We need to treat the anode and cathode separately. I believe I have the anode up here first, yeah. So at the anode, something has to oxidize. It can't be the sodium ion because sodium is already a positive 1. It doesn't go any higher than positive 1. But the chloride ion could oxidize. And since you have water in here now, remember you've got sodium ions, chloride ions. It's a solution, so there's water in there too. And water can definitely oxidize and reduce. So the oxygen in water is a -2 oxidation number. That could oxidize to 0 and make just elemental oxygen. Yesterday, in the back of the room, I was electrolyzing water, if you remember. I had that power supply. It's gone now. Mr. Hevel is making hydrogen to... Next door in the Chem 1 class, we're blowing up eggs. I hollowed out some eggs, and so in a moment, you're going to hear what sounds like a gunshot, and probably some students responding. That's just Mr. Hevel. So anyway, you know that water can oxidize and reduce because we saw the water oxidizing and reducing yesterday. There was one cord that had a cathode and one cord that had an anode, and so both things were happening. We were generating hydrogen in one tube and oxygen in the other tube. They were coming up. So as long as you have water, water can always either oxidize or reduce. To figure out which one actually happens when you have salt water, you'd take that reduction potential table that you have. Would you take that out? We're going to have to compare the oxidation potential of chloride ion to the oxidation potential of water. Now remember that we're talking oxidation here, so these are all written as reduction. So we need to find these things in the product on this paper. The oxidation of chloride is, it's almost halfway down. I'll put my finger next to it so you can find it. It's right there. Find the oxidation of chloride. See it? Now remember that thing's got to turn around. So the oxidation potential is -1.36 volts. You see it? So chloride is not very willing to oxidize, as you see. Its oxidation potential is -1.36. Oxygen in water, now this is water that would be oxidizing. The water is only a couple away from the chlorine. Let's see, it's 3 reactions away from chlorine. I'll put my finger next to this one. Come on. Oh, yeah. I made the mistake. I was looking for it in the reactants. You got to find it in the products because it's water oxidized. You got to turn it around. So right here, it's almost the exact middle of the table in the first column. So this is the oxidation of water. And notice the product of that oxidation is oxygen. Remember, turn that reaction around. Anybody need one of these? Y'all have yours? Now, notice that when water oxidizes, the oxidation potential is -1.23. So neither one is very excited about oxidizing. This is the data that we have to work with. So you got chloride that doesn't want to oxidize, and you have water that doesn't want to oxidize. So which one does oxidize? It's going to turn out that when you have 2 bad choices where both of them are negative, choose the more positive one. Even though they're both negative, which one is more positive? The one that's more positive in this case is water. So at the anode, where oxidation has to occur, it's going to be water that's oxidizing. So what would we observe? We would observe oxygen being made at the anode. You'd see bubbling of a clear substance. That's the oxygen that would be bubbling out. And that's what it says down here. Water tends to oxidize before chloride because its oxidation potential is more positive. So we had that comparison of what happens at the anode. Now we have to turn it over to, okay, the other side. What happens at the cathode? At the cathode, reduction has to happen. So we have sodium ions and chloride ions and water molecules. What in that three substances could possibly reduce at the cathode? Can sodium ions reduce? Could sodium ion reduce? Sodium has a positive 1 charge. Could that positive 1 go down at all? I think it can. Sodium, you always have the opportunity to take an element and make it the elemental form of it, which has 0 charge. So sodium being a positive 1 could go down to 0 in its oxidation number. It would have to gain an electron, that it would have to reduce to go to 0. So sodium actually is a possibility for what happens at the cathode. Can chloride reduce? So chloride here is a negative 1. Can chloride go any lower in oxidation number than negative 1? In that case, no. Chloride is negative 1, and it doesn't go any lower. It can go higher. It can go to 0 or even positives because you've got the chlorate ion, chloride ion. But it can't reduce. So sodium might, chloride won't, and water could too. So we need to compare the sodium ions reduction to water's reduction. Now, find sodium reducing on here. And I'm going to point at it right now with my finger. See where it is? Sodium is very stable as an ion. It is not at all interested in reducing. It's got a reduction potential of negative 2.71 volts. 2.71? Yeah. And then water, reducing. We're looking for water now as a reactant. And I'll put my finger next to this one. It's just up from sodium. It's right there. Oops. Yeah, right there. Find it? The hydrogen in water is positive 1, and so it reduces to H2. So, there are the two possibilities of what can happen at the cathode. Was that it? Did I just hear Mr. Hubble? No? Okay. Is that Grace dropping something else? So now, once again, we have two bad choices. Neither one of these two reductions is interested in happening. However, electrolysis is forcing this to happen. So what is going to happen at the cathode? The one that's more positive is what's going to happen, which is the water. So we wind up electrolyzing sodium chloride solution, and the sodium and the chloride don't do anything in this setup. The water oxidizes and the water reduces, because in both cases the water has the higher potential. When I say higher, I mean more positive potential. And this is often the case because, remember, electrolysis is the forcing of a non-spontaneous reaction to occur. Electrolysis causes reactions to occur that don't want to occur. They're non-spontaneous. So yeah, expect to have bad choices here of what has to reduce. It's the one, you're going to have two negatives, just choose the one that's more positive, or less negative. Okay, any questions that I can answer about this? This is kind of confusing, I get it. The next slide, I have a couple other examples to do just like this one.